Hello and welcome to Computer Science. So this is just a video to kind of run you through these practice problems and make sure that you're on the right track. So suppose programs A, B, C, and D are in memory. They occupy partitions of size 100, 300, 75, 75, and 210 as shown below. Suppose programs A and D terminate. Draw a picture of what memory looks like after removing them and label the start and end of each empty and occupied partition. All right, so we're getting rid of A and D. All right, so those programs are going to terminate, which means that we now have sort of a blank empty space from 150 to 250. This is now empty. All right, we still have program B, which goes from 250 to 550, which means it's eating up 300 kilobytes. All right, program C is still there, which is eating up 75 kilobytes. So that brings us to 625. Program D has been terminated. So now we have some empty space right here. All right, and specifically we have 75 empty space. Here we had 100 empty space. Program E is still active. So this was going to 700. This is going to 910. E is still active at 210. And then we have some empty space at the end here. All right, and specifically we have 90, which would bring us to 1000 right there. All right, so that part's pretty straightforward. You're just basically unshading A and D. The real question is part C here. New programs F, G, and H start running in that order. Use the best fit algorithm to place them into memory and draw what memory looks like afterwards. All right. So again, they're showing up in this order. So when we're figuring out the best fit, it's not like, let me put them in the best order and fit them that way. It's what's the smallest space available that's going to fit this size 70 kilobyte program. So we have empty spaces of 100, 75, and 90. All right. The smallest one that's going to fit is this size 75 right here. All right. So C is going to go inside of here. And let's see. Let's draw that right in here. We'll start that right here. So this was 625. And now all of a sudden we have a new one in here that's F. All right, so F is right here. It's 70 kilobytes, so it goes from 625 to 695. Then we have a little bit of empty space right here. All right, so this would be empty. And it's only going to have 5 kilobytes in it, which is going to bring us to 700. All right, so you're kind of seeing the effects of best fit right away is that it ends up creating a lot of these empty spaces that are really tiny that we then usually can't use and get wasted. All right, so there's the first one. Let's see. We can draw in the other ones that are still active because obviously nothing's happening there. So these are still active, so we can put in B, C, and F. So there's B, there's C. This one's 300. This one's 75. F we just did. That's 70. What else do we have? We've got this 5 empty one. And then on the other side of that, we have E, which is 210. Okay. All right. So let's see. Next, we have G is 50. So it's not going to fit in this 5 space. We've got 100 and we've got 90. All right. So again, we're going to use the smallest space that still fits it. So that's going to be this 90 over here. So G is going to end up right next to E. All right, so this will be G. This is going to take up 50, which means we've basically got 40 left over right there. And then we get to H. 35 kilobytes. We've got 40 left over here, so it's still going to fit. So we can put H right here, which is our 35. And then we're going to have another 5 that's empty right here. All right, and then this stayed empty. We never used this one. So this is still 100 kilobytes. And then we can just go through and label all these. So this is 150. This must be 250. This must be 550, 625, 695, 700. This one has to be 910, 960, 995, and 1000 there. All right. But just kind of going through and saying, all right, best fit means I'm using the smallest available that will still fit it. So again, the first one was 70. So the smallest available one that worked was that 75 that just freed up. Then we got to 50. So the next smallest one that worked was the 90 here. That created a size 40 and a size 100. Luckily, the 35 fit in the size 40. And then we just had the 5 left over right there. So we end up with an empty 100 kilobytes here, an empty 5 here, and an empty 5 here. Okay. Let's take a look at this one. Suppose programs A and C are in memory as shown below. The new programs 200, 150, and 50 start running in that order. Use first fit to place them into memory and draw what it looks like afterwards. All right, so first fit, much like the name says, is taking the first available empty space and putting it into that spot. All right, so that will fit it, obviously. So we've got 300 at the start. 300 fits this 200 kilobytes. So we're going to put this F right here at the start. There's F. We're using up 200. We're going to 450 here, which means we've currently got size 100 there. All right. We get to G, which is 150. That spot is too small. So we're left putting G over here on the other side. So that's going to be our 150, which is going to bring this to 775. And then the last one we have left is size 50. Okay. We've got 100 left over here, so that will fit right in here. So we can say, all right, this is our H, which is using up 50, which means this is at 500. So we've got F and H right next to each other. We've got a gap, 500 to 550. We've got C right here. We've got G. And then this 775 to the end here is empty all the way to 1,000. So we've got 225 left over. All right, and this one right here is also empty. And it is size 50. All right. So again, just being able to recognize the different types here and then what they imply. All right, but this is what you should be getting for this one. All right, last memory allocation technique. So we've got our memory again. This time we're using worst fit, which again sounds weird, but it's basically you're using the biggest, emptiest space possible. And the goal there is that you're not, dividing up and leaving lots of tiny little bits of memory that can't really be used all over the computer. So F is 40 kilobytes, but again, we start by using the biggest possible space. So that's going to be over here. We're going to put F right here. We're going to use 40 kilobytes. That's going to bring us up to 665. Then we're going to move on to G, which is size 70. Now we got to kind of keep track here. So after we put this one in, this one's 300. This one only used up 4, so it's still 335 compared to 300. So this is still the bigger section right here. We're going to put in a size 70 program. So that becomes G right here. All right, this is going to use up 70, which is going to bring us to 735. All right, which means we now have 265 left over here compared to the 300 that we have left over here. We get to the last program, which is 150. Again, both of these will fit. It'll fit in either one of these, but we use the biggest possible one. So we're going to use this one right here. We're going to put H inside of this. It's going to use up 150, which is going to bring this one to 400. So we've got 150 space here that's left empty. And then we have a 265 space here that's left empty, bringing us up to 1,000. So again, worst fit, the name seems kind of weird, but actually it usually ends up leaving us the biggest sort of chunks of memory left over, so that we're not left with a whole bunch of tiny little slivers like we had with best fit. All right, when we did best fit, you had 5 kilobytes there, you had 5 kilobytes there, probably not large enough to be very useful. All right, in comparison, here we had 150 kilobytes, 265 kilobytes, much more flexible, much more able to run all sorts of programs. All right, and then the last thing that we talked about today, memory management with address binding. All right, so again, when we wrote our assembly code, we kind of said, okay, load it as 5, load it as 6, load it as 4, and we said these were our addresses. And those are the logical addresses. But when we actually put them into memory, address 5 might be the operating system. So we can't just kick out the operating system and load our program. So you really almost have to think of these as an offset. All right. So load 5 is really like, okay, load X plus 5. Compare 6 is X plus 6. Jump greater than 4 is like X plus 4. Output 6 is like X plus 6. And then it's just a question of what is our X? Well, this says, suppose the program on the left gets put into memory partition that starts at address 32,600. For the program to run properly, each logical address needs to be replaced by the physical address. So this becomes load, and instead of load 5, it then becomes load 32,605. All right. This becomes, instead of compare 6, we're always going to keep plugging in this 32,600. This becomes our X. So now we're doing compare 32,606. Then we're going to jump greater than to 32,604. And then we're going to output 6, but that really becomes output 32,606. This next one is just halt, so that can stay the same. And then our data now is actually in 32,605 and 32,606. All right. So again, this is how we write it as programmers. And then the operating system says, okay, well, they're really looking for the instruction or the address 5 down or 6 down or 4 down. So let me just take the starting point and say starting point plus 5, starting point plus 6, starting point plus 4, starting point plus 6, and kind of translate those over to physical addresses on the actual computer memory or the RAM that we're interacting with. Okay, so these are sort of the main, 4 things that we covered in the notes today. These are the things that you're going to need to know for the homework, you're going to need to know for the eventual exam, is this idea of address binding, and then being familiar with worst fit, best fit, and first fit, and being able to take memory and say, okay, if this algorithm is being applied, this is how it's going to end up, or this is how it's going to end up, or so on and so forth. All right. So hope this was helpful. If you have any questions, just let me know. Otherwise, have a great day.